Hi everyone, today we're going to be talking about topic 7.7, calculating the equilibrium concentrations. So we've already seen some straightforward examples of trying to calculate K when you're given all equilibrium concentrations. So here's an example. We have this reaction PCl5 decomposes to form PCl3 and Cl2. We're given the concentrations of each at equilibrium and we're asked to find K. Firstly, we write out expression. K is equal to concentration of PCl3 times the concentration of Cl2 divided by the concentration of PCl5, right? Products over reactants. This is equal to 0.040 times 0.080. Again, units don't really matter here because they all cancel out. Divided by 0.200. And here we get the equilibrium constant is 0.016, or the reaction would prefer to go to the left versus the right. And so that's quite a simple example that we've seen so far. We can also get an example like this, where we're given the equilibrium constant and we're given some equilibrium concentrations and we're trying to find the equilibrium concentration of something else. So here we want Br2, we're given HBr and H2, and we know what K is. We can write our expression for K, that's equal to the concentration of HBr squared, divided by the concentration of H2 times the concentration of Br2. We can plug in some values here. We know HBr, that's 0.35, and that has to be squared. We know the concentration of H2, that's 0.22, and we're trying to find the concentration of Br2. All this should be equal to 62.5, and again, all we need to do here is some simple algebra. And the concentration of Br2 should be 0.0089 if we have the right number of sig figs. So again, a pretty straightforward example. If you're given some of the values, all you need to do is solve for x. Now, of course, all the examples we've been looking at so far were given the concentration at equilibrium. But what happens if I don't have that concentration and I want to actually find that particular concentration? So let's say if I have the initial, let's say I'm given the initial concentration of reactants, and I'm asked, what is the concentration at equilibrium? You might imagine that we can't really figure this out that easily with our expression of K because, well, we don't have anything to plug in because we don't know the concentration at equilibrium. But there's something that we can use, which is known as an ICE table, which helps us solve these problems and do a little bit of algebra. ICE basically stands for I is initial, where you plug in the initial concentrations you're given. C stands for change. Sometimes you're given that a concentration may change a particular molarity, or you can estimate this doing a little bit of algebra. And then E is equilibrium, which is basically the concentration or the pressure when you reach equilibrium. You can use these tables in order to diagnose problems like this. Sometimes you'll also see this being written as a RICE table, where all the rest is, ICE stands for the same thing, but the R basically just means reaction, where first you have to write your reaction. And so we'll use RICE tables, but you may also hear ICE tables, since that's what, more commonly used as well. And so there's a few different cases where you use ICE or RICE tables. One is if you're trying to solve for K and you're given the initial concentrations or pressures and one equilibrium concentration or pressure, but you're not given all the information. The other one is if you're trying to find the missing equilibrium concentration, you can use a RICE table. Also, if you want to find the equilibrium concentration, but you're given initial concentrations and K. All of these are pretty useful to employ RICE tables. So let's look at this example here. We're given this reaction, H2 plus I2 makes 2HI. We're given the concentration of H2 and I2 at the start of the reaction, and so this is essentially initial. So they add both these together in a 1 liter flask, and they're asking what's the equilibrium concentration, assuming that we know its equilibrium constant of 55.3. So we know that we start at 1 mole per liter, which is 1 molar for each of them, and so we know that already. We know that we're not given the concentration of HI, and so at the start of this reaction this should be 0, and we know our equilibrium constant Kc. So if we're going to write this out, essentially, we should write this as our table. And I'm actually going to scoot this down so we have a little bit more space. But we have R, which is reaction, I is initial, C is change, and E is equilibrium. And so for our reaction, that quite simply is H2. We'll have a column for H2, plus I2. We'll have a column for I2. And that is in equilibrium with 2HI. Now let's try and fill in the rest of this table. Initially, we've been given initial concentrations. This is 1 molar, or it's 1.00 molar. I2 is the same. And for 2HI, we know this is 0 molar because the reaction hasn't proceeded at all. Now let's think of change. We don't know exactly how much this has changed, but we know at equilibrium, we've had some sort of change. Right? We know that our reactants, and this is at equilibrium, we know that for our reactants, the concentration should go down, and for products, it should go up. So what we know is that the concentration of products, of reactants, should decrease by some factor. We can call that factor X, and since it's decreasing, it's negative. We know that because we have the same coefficients here of 1 for I2, that should be exactly the same. Right? Their concentrations are going to go down equally because they have the same stoichiometry. And we know that products are going up, and so we should just have positive X here, but because our coefficient is 2, we know that that should change by twice the amount. So we start with 1 molar each of H2 and I2. That's in equilibrium with 2HI, and we started with 0 molar HI. We know that we've reduced H2 and I2 by some amount, and we have to increase HI by that same amount, but we have to also factor in this factor of 2. And so now let's look at equilibrium, right? If we just add these two together, and I'm going to add a blue line here, we know at equilibrium we start at 1.00 molar, and we reduce it by some amount, X. That same thing is true for I2. And for 2HI, if you add these together, it's just 2X. And so now using this, we can use this last part of our table here, the equilibrium, and now we can think about K. Right, we've been given K, and that's 55.3. But we also know that we can write an expression for this. We know that Kc is going to be equal to, if we look at our equation, it's products over reactants, concentration of HI squared over the concentration of H2 times the concentration of I2. And so we know this initially, we could figure out the reaction quotient, but at equilibrium, we've shown that we can make this expression using this. Even though we don't know these exact numbers, we can plug in what we have written here. So the concentration of HI should be 2X squared. Concentration of H2 should be 1.00 minus X. And the concentration of I2 is also 1.00 minus X. And if we want to rewrite this, we can just think back to algebra. This is just 2x squared divided by 1.00 minus x, and that whole thing is squared. And that equals 55.3. Now, all we need to do, if we want to find the concentrations of each of these, is just solve for x. So we're basically just doing algebra. First thing we can do is take the square root of both sides. This essentially ends up, and I'm going to write this over here, as 7.436 is equal to 2x over 1.00 minus x. We can multiply the denominator on both sides, and we get 7.436 minus 7.436x equals 2x. We can add 7.436 to both sides, and we get 7.436 equals 9.436x. And then we're basically just solving for x here, which is 0.788. So we're not done here. There's one more step that we have to do in order to complete this, and that is plugging it back into our equations that we determined up here. And so if we want the concentration of I2 or H2, right, we know that those two are equal to each other. and it's equal to 1.00 minus x. So it's 1.00 minus 0.788, which is equal to 0.212 molar. And if we want the concentration of HI, that is just concentration of HI is 2x, which is equal to 2 times 0.788, which is 1.58 molar. So if you want to find the concentrations of these at equilibrium, you can go through this Rice table process, and this will always work if you're given initial concentrations or if you're only given some data and you want to see what's happening at equilibrium. You can essentially do all this algebra and solve for x. Then once you get to the bottom here, all you need to do is plug back in. And so if you're not brushed up on your algebra skills, I suggest doing a little bit of practice to kind of help you out with this, since a lot of this ICE table is just algebra. Now, there's one quick assumption that'll make your life a little bit easier on some problems, and we'll talk a little bit more about this in class so I can better illustrate this. But let's say x is very small, and we have an example like in the previous one where you have 1.00 minus x. If x is really small, or less than 5% of the value that you're subtracting it from, you can essentially ignore x. The reason for this is because it's not going to change the value so much differently. For example, let's say I have 1.00 minus x, and after I do all of this work, x is equal to 0.000001. Well, then all this ends up being is 1.00 minus x is just equal to 0.99999, which isn't really going to change your value all that much, and you might as well just use 1. And so if your x value is really small compared to what you're subtracting it from, you can essentially ignore it and then continue on with your algebra, and you get the exact same answer. So there'll be some examples of this, but for example, if you're doing, like in the other, like in the problem I just did, right, if it's HI is equal to 2x, in this case, you cannot ignore x. Right? It's only if you're subtracting x from some larger number and x is very small that you can just ignore it and continue on with your algebra. And so you'll see some examples of this as we go on, but it's something to keep in mind to make your life a little bit easier. You can technically not ignore it and get the same answer, but you end up saving yourself a lot of time by using this assumption. We'll do some more practice of more complex examples like using the quadratic equation in class, but for now that's all. Thanks, guys.